At the last lecture, I was telling you about the amazing concordance of Earth's weather with sunspots. This is something that is not accepted by the climate community. Nobody really has a clear explanation for it. The energy is not there. It's not an energetics matter. Anybody who wants to study the problem should talk to me, and I can tell you what to read. I worked on the problem last year for a while and gave up. I couldn't solve it, couldn't figure out what was going on. But there are some things that might be related. One of the problems that climate scientists have in predicting weather climates is the cloud cover on the Earth. If the cloud cover goes up, reflects more light off the surface of the Earth, and the Earth is colder. But predicting the cloud cover and what the cloud cover would do is difficult. With the when the sun gives off a lot of cosmic rays, it expels a tremendous amount of magnetic field energy, just floats in space around us. That field energy serves a purpose. It tends to make high energy particles gyro around, and they don't collide with the Earth as much. Does that have anything to do with weather? Well, that's very controversial. So, okay, let's start talking about astronomy again. The astronomy we've covered so far is basically everything in our solar system. We've covered all the planets, the sun, that's about it. But we've not talked at all about all these stars. Okay, so we're going to zoom out from the solar system from 1 astronomical unit to a radius of 10 to the 4th, 10 to the 5th astronomical units. It gets up to 10 to the 6th astronomical units. And as we speak, we're going to go further and further and further from the Earth. That means that we are going further and further from any common understanding, your intuition, probably your good intuition. I'd be surprised how that can lead you astray. But I'll go ahead and talk about this now. Okay, so when you study stars, this is a picture taken of a star field in the galactic plane. You know that milky part of the sky where the band of sky... Has everybody seen the galactic plane? Who's seen it? Jeez. The rest of you have not seen the galactic plane. All right, this is an assignment for everybody. Leave Berkeley. Leave the area. Go where it's dark at night. And look up. And those are not... There's a magnificent band of Milky Way up there. That is our galaxy. And if you look at it, you can't resolve it with your eye. It's all just a uniform white blob. But if you look at it with a telescope, you do resolve it into lots and lots and lots of stars. Okay? Now these stars are in our galaxy, and the question is, how far away are they? Are they all the same distance? Are they all the same brightness? All these questions. So how do we go about answering those questions? Okay, first I want to ask a question of you. we talked about the sun and an H-bomb. All right, what's the difference between the sun and an H-bomb? Anybody? Why does an H-bomb explode and the sun doesn't? Why doesn't the sun explode just like an H-bomb? Anybody? Volunteer? Anybody want to answer? Why doesn't the sun, it's got an H-bomb going off, tremendous energy. Why doesn't it explode? Why are we safe from a nuclear explosion in the sky? Anybody? Yeah. Gravity. Gravity. There is tremendous force of gravity on the nuclear reactions taking place. If they try to explode, they've got to push against the whole gravity of the sun. It weighs a lot. They can't get anywhere. They push and push and push, and the gravity pushes them in. It's a constant battle where the gravity opposes the pressure exerted by the tremendous energies given off by the sun. Now that's why the sun is stable, in effect. You can't overcome it. And this is what happens in the universe. What will happen if we don't have if there's no energy generation in the sun? Well, gravity is going to win because there won't be anything opposing it. Gravity pushes, 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 and doesn't let go ever. So the push of gravity is really important for making some of the most bizarre objects in the universe, which we'll talk about. All right? All right, but what in the center of the sun, what kind of radiation is present? Do the sun and H-bomb both generate lots of gamma rays? Feedback of a star is needed so it burns steadily. They both are burning hydrogen and helium, or is it all of the above? What do you say? Hold a card up. A few of you got to vote. A few of you vote. Well, talk to your neighbor. Come on, I want you to talk to your neighbor. Most of you don't have a card up. Come on, stick a card up in the air. I don't care if it's wrong. Tell me if it's right or not. I want to see if you understand what I've talked about yesterday or Tuesday. Come on, stick a card up. Something. Come on, let's go, let's go. We've got a lot of stuff, neat stuff to show you today. Do you have a card? There's some extra cards here, if you want them. Okay. It's true that they are both burning hydrogen to helium. That's really what an H-bomb does. It takes hydrogen and converts it to helium and gets a tremendous amount of energy out of that. We'll talk about the energy in a moment. But it doesn't have any feedback. So the star is absent a massive force of gravity pushing it in. So that's true. And they both generate lots and lots of X-rays because at the huge temperatures this is reacting at, the thermal temperature is gamma ray energy. Huge energies. It would kill you if you could get near it, but you can't. The whole sun degrades it. So the answer is blue. All of the above. Most of you most of you got that right. Okay. Now, let's talk about distances to everything. This is something that reviewed. We did this in detail. If there's a star here and it's putting out some energy, at 1 astronomical unit, the energy through this window is the same as through this bigger window. That is, the total energy is the same as through the bigger window. All right, so that means that that the inverse square law is correct. The area of this thing grows as the distance squared. And that means that the flux per unit area, the energy crossing across here per window pane, falls as the distance squared. That's essential. The total circumference, the total area of a sphere, you learned in high school geometry, is 4 pi times the radius squared. All right. All right. So the amount per unit area declines as distance squared. Fainter. Now, you apply this to stars. Stars that don't have a big apparent brightness are, you would think, they're faint, and therefore they should be further away. The ones that are bright should be closer. And that's correct, except for the fact that they don't all have the same brightness. The intrinsic brightness of a star is a function you have to understand to make that association. All right, so the apparent brightness is the first thing you can observe. You look up in the sky and you see all these guys that are faint. Some are bright, some are faint. So that's one way astronomers can measure the sky. Okay, the apparent brightness is the luminosity divided by 4 pi d squared. 4 pi d squared is the area of a circle. And the units of brightness are in watts per square meter. The watts, here, this is a square meter. Watts is the unit of energy per unit second. And that tells you how much power is flowing through a window. All right, that's essential. Now, another thing we want to do is let's review the issue of parallax. If the star is close up and the background stars are way back here, you know that the parallax between two opposing views of what we see in June and July, and June and August and December. For example, this could be the December view of this star, and this star is not in the same place as it is in June. It moved a little bit. And that's what we call parallax. All right, the baseline here is 2 astronomical units, twice the distance of the Earth to the Sun. The parallax is the angle subtended not by the total baseline, but by 1 astronomical unit, half the distance, half the diameter of the Earth's orbit. And that's the parallax. Now, for strange reasons, that the parallax is, as the distance d increases, the distance to the star goes up, the parallax of it decreases, clearly. So if it's real close, you have a big parallax. If it's real far, you have a small parallax. Well, that's something you're all used to. Okay. All right, so the distance at which 1 astronomical unit, the distance from the Earth to the Sun, subtends 1 arcsecond is called 1 parsec. That's just what is defined to be a parsec. And it's parsec written PC. Why the hell is written PC? I don't know. Anyhow, it's written PC for short. All right, and that's just notation astronomers use. Okay, now that is a unit of distance. You go out 1 parsec, and you will have a parallax of 1 arcsecond. Now, how far is that? It turns out to be 3.26 light years, and it's about, not exactly, but it's about 200,000 times the distance of the Earth from the sun. 200,000 astronomical units is 1 parsec. All right, so let's see what we see. Now, the distance in parsecs is 1 over the parallax it has. Okay, if it's a half arc-second parallax, then the reciprocal of it is 2, and that means the object is 2 parsecs away from the Earth. All right. Now, the sun. Let's measure nearby stars. The nearest star has a parallax of 0.73 arc-seconds. It's a triple star known as Proxima Centauri. It's part of Alpha Centauri. That's a bright star it's in the southern hemisphere. You can't see it from here. Okay, this is at a distance of 1.3 parsecs, and that's 4.1 light years, 4.3 light years. That's the nearest star. So if you wanted to go visit a star, get in your handy-dandy spaceship and go at spaceship speeds, you ain't going to get there by Sunday. It is a long way. That's the nearest star, 4.3 light years away. Now, the number of stars that are close to us, within, say, 30 parsecs, 30 stars are known within 4 parsecs. We can see them, and they are all faint. Faint red dwarfs. Now, red dwarf meaning the star is red. A dwarf means it's smaller than the sun. That's all it means. That's what a dwarf means. Is the sun's class or smaller. Okay, now the brightness. So let me classify the brightness. The brightness of a star is, first of all, I'm going to call it B instead of using this idiotic system called magnitude. Stars are classified as magnitudes. Have anybody heard of the term magnitude for a star or magnitude for the apparent brightness? Okay, good. You're not real astronomers then if you haven't heard that idiotic term. Magnitude is, you'll see, if you read any literature, you'll see this idiotic notation. Magnitudes are a logarithmic scale. And it's also, large magnitudes are faint, and bright objects have small magnitudes. It's got a negative sign in it, and it's insane. 5 magnitudes means a factor of 100 fainter. So, okay, you can use that. Apparently, it's something the Greeks first, or Hipparchus first made it up. I don't know exactly its history. All right, you can see Wikipedia if you want to see details. Look up astronomy, magnitudes. And it's all defined there. But we don't need it. All right, so, all right, we're going to use this, brightness. And the brightness is the luminosity of the star, total energy per second, that's in watts. That's the total output of the sun, for example, divided by 4 pi d squared, and d is the distance. So this is just a classification of the familiar brightness law, the inverse square law by that. Okay, now you measure the brightness on CCD, put it behind your telescope. A CCD, remember, is your detector that's in your camcorder. And the camcorder can record the number of electrons. You know, they can tell exactly how bright the object was. You can read off magnitudes when it's calibrated. So that's fine. Okay, now, so that is a first observable. First is the brightness. Second is an observable I'm going to call the space motion. Space velocity. Okay, space velocity. And the space velocity is something you determine by measuring the redshift of the lines. If the lines are redshifted, that tells you something. If they're blue shifted, it tells you something else. And so you can measure redshifts of a lot of these lines. Okay, and you can also measure the proper motion of the object. Proper motion is the parallax it has all the time. You can see a star here wander across. And you see the angular change of its position. And that angular change is called the proper motion. Now, the stars pretty much don't have any proper motion you can see. But there is a star that can be seen. Now, the proper motion is an angular speed. I see the star moving 5 arc seconds per year, for example. And that is the angular speed, and that's what is proper motion. If you measure its radial velocity from you by measuring the Doppler shift, okay, and you see the proper motion, you can infer its distance, and you can infer the three-dimensional distance of the star. And stars are all moving relative to the Earth. They are not fixed in space. The entire galaxy is rotating, and more than you can see it move with difficulty. Okay, so you can really measure the third three-dimensional space velocity. Now, there happens there's a famous star known as Barnard's star, and it has a huge proper motion. It's moving 10.3 arc seconds per year. You can see it. If you take a plate 1 year, or take a CCD picture 1 year and take it the next month, you can see it move. There's only a few hundred stars that have proper motions greater than 1 arc second per year. All right, but Barnard's star is the winner. It has 10.3 arc seconds per year. So it's really moving fast. Now the star happens to be close to us, and it's moving. The galactic plane is shaped like this, and the star is moving fast the other way. And it's close to us, and we can see that transverse motion is a proper motion, it's called. All right, so you can measure one way or another, you can put together the real distance to a few stars. Using this parallax, you measure the distance to the star, and the proper motion, you get inferred distance, and Doppler shift, you learn the distance as well. And so for a few stars, you can really measure the distance. All right, so now the next is the issue of binary stars. Here is the Big Dipper, and this star right here is called Mizar. You all seen the Big Dipper. All right, where's the North Pole? The North Pole is up here. It's pointed to by the two stars. It's up here about. All right, so the Big Dipper has a star that's right there. And this one is a visual binary, A and B. Each of the stars is a binary. So it's a binary and binary. It's kind of crazy. But you can see it change if you take pictures a little later. Okay, so now we use Kepler's second law to measure the mass of the planets. By being in a binary orbit, we're able to infer the mass of the sun. And that's very, very powerful, of course. That's the only way we can directly measure the masses with Kepler's second law, which you know. Okay, now they're wide enough separated, this visual binary, we will see some visual binaries in the telescope. Did you see the Cal star? Okay, that's a visual binary. All right. All right, and let's see. Okay, there are all these different types of binaries. Spectroscopic binary. You can see it's a binary because when you take a redshift of it, the lines are moving back and forth. That's a spectroscopic binary. Eclipsing binary, one star, it comes right in front of the other and blocks the light at the right time. This is something, this is what you use, of course, to look for, this is what Kepler is using to look for planets. You look at the occultation of the bright star. Optical doubles aren't really related. They just look like they're related, but they don't really, they're not at the same distance. Okay, so here's an eclipsing binary where one star comes in front of the other. This is a little fainter because a little bit of the orange star is blocked out. Here both of them are seen, and here the blue one's completely obscured and makes it deeper. Visual binary, we'll have them. This is a pair. I think this might be the Cal star. I'm not sure. This is their position, 1900, all the way through 1970. It really is moving around. And you take pictures like this, and you can infer the mass of the planets, of the moons, I'm sorry, the mass of the stars. All right. Okay, that's how you use them. Another is spectroscopic binaries. We talked about this as well. If one star is moving towards us, the lines the lines from it will be blue shifted. If it's moving away, it's red shifted. Here, this is very exaggerated, but here, this line is this. What the hell is it? It must be this line. So this shifts. Yeah, this is this line, and it shifts back and forth as it moves. Okay, all these binaries can be seen in the sky, and they allow us to measure properties of the stars. Okay, so let me try to show you a little bit of one. Okay, so here, star A and star B, all right, they're orbiting each other. The Earth is over here somewhere. This is a large system. Now, as it comes in, it's blue shifted. Now it's red shifting, blue shifting, red shifting, blue shifting. Just goes back and forth, and by this method, you can measure the mass. And this is the method we used earlier in the course. All right, so this is incredibly important to do this. Okay, now. Okay, so usually you see just one set of lines. You don't see two sets of lines, but it's okay. And they move back and forth about an unseen companion you don't see. Kepler's second law, I just don't worry about this. This is the form it took. That p squared went as the radius to the third power. P is the period divided by the mass. Note that 2 pi times the radius is equal to the period times the velocity. The period square, and so let's substitute that here. Take the r out of here, it's equal to this. That's p squared and the velocity. So we measure the period and the velocity. And therefore, we've got all these, this is known, this is known, this is known, and the only thing unknown is the mass. So you solve the equation for the mass, big M. And so that allows us to solve, that is the only way we measure mass. And it's important to do that. We want to know what it is. All right, so what else can we say about stars? The other thing you can say about stars is the brightness of the star. How bright is the star? Well, it has an area All right, there's an area, R. Okay. And in each patch of the star, there's a temperature. Temperature at each point of the star. Now, we talked about the area. The total area of the star is 4 pi times the radius squared, same as before. And the brightness of a star, remember the black body equation I said. The brightness of a star, the flux, equals sigma t to the fourth. Sigma is some constant. It's just a number. Doesn't matter what it is. But it goes as the fourth power of the temperature. So that is the emission per unit area. This times area, emission is energy per second per square meter. So you multiply times the square meters, 4 pi r squared, and you end up with energy per second. All right, so the total luminosity of a star is 4 pi r squared times sigma t to the fourth. This is necessary to solve some of the problems that you will have in the next problem set, or some of this problems. All right, so the Stefan-Boltzmann law was used to derive this, and it will just say that that's what it is. That's approximately right. It's not exactly right, but stars are approximately black bodies, and so we use the black body emission formula. Okay, now that's simply saying luminosity equals the surface area times the energy emitted per area. Okay. So to put it together, for example, we might have the distance to that star. And we know we're trying to infer the absolute luminosity of the star from a measurement of the flux that we see on the Earth. All right, now how can you measure temperature? How do you measure temperature of anything? The temperature is determined by the color. If it's blue, the temperature is hot. If it's red, the temperature is colder. And you can infer the temperature pretty well with the accuracy of the black body formula. You just have to know the color of the star, and it tells you what the temperature is. All right? So the only thing you don't know then is the diameter of the star, or the radius of the star. But you can solve for it. You know the absolute luminosity because that is inferred from the distance. And temperature you inferred by the color of the star. And so the only thing left is the radius of the star. So you can solve for that too. All right, so that's one thing you can measure. Stellar properties, temperature, you can measure by looking at the star. Yow. Didn't break it, I hope. Okay, so you measure the colors, and that tells you the temperature or the spectral features. All right, you measure luminosity from the brightness of the object and the distance of the object, which you infer in one way or another. The radius, r, you infer from the luminosity and the temperature using this formula. This formula here. All right, if you know L and T, you can solve for R. Okay, the mass can be found in a binary orbit if it's a favorable situation. Sometimes you can do it, other times you can't. All right, and then finally, there is something called a spectral classification. And this is something we'll talk about now. Spectral classification has an interesting history. O, B, A, F, G, K, M. that's different classes of stars. Our star happens to be a G star. You didn't know that, but we're a G3 dwarf. That's the star. And here's how you remember it. Oh, be a fine girl, kiss me. Okay? Oh, be a fine girl, kiss me. And that's the order of the stars. Now, this one's hot, colder. This is hot, 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 colder, colder, colder. The M stars are very red. The O stars are very blue. And oh, be a fine girl, kiss me. You can help remember what sequence is what. Now, what the hell sequence is that? All right, each type of star is divided up. Each of these stars, G stars, divided into categories 0 through 9. And they stick all these numbers on. So the sun, oh, it's G2. I thought it was G3 dwarf. Anyhow, the sun's G2. Okay, we'll call it G2. All right, and then finally, the type is then subdivided into luminosity classes. 3 is a giant, 5 is a dwarf, 1 is a supergiant. So what kind of star are we? We are a G2 dwarf. That would mean if you see it in the literature, it'll say G2-5. We're a dwarf, believe it or not. The sun is dwarf. Okay, so let's see what that means. All right, first of all, here are spectra of a bunch of stars. These are spectra from the blue at 400 nanometers, or 4,000 angstroms, to red, 700 nanometers, 7,000 angstroms. All right, now, this is a continuous spectrum, but it has lines in it. Lines, lines, lines. And different stars of different classes have different amounts of lines. M2 stars have a strong line of sodium. It also has lines of titanium oxide, magnesium hydride, iron, calcium, cyanogen. All these lines are identified in those stars. And as you look at a star that's very blue, the stars have very few lines. Very few. You can barely see anything here. As the star is a little cooler, you start to see lines of hydrogen. Take this one. The A0 line is where the hydrogen lines are strong. These are Balmer lines. Who knows what the word Balmer means? Balmer. It's somebody's this is proper name. For all of you who did study chemistry, in chemistry, there is 1, 2, 3, 4, 5, 6. This is n equals 1. Let's see, energy. N equals 1, 2, 3, 4, 5. Okay. The Balmer lines are lines that go from here to here, or here to here, or here to here, or here to here. The Balmer lines mean a transition from the first excited state to the next excited states. How many of you know what I'm talking about? Okay? The rest of you don't worry. But this is chemistry talking. All right, so the star to have absorption in the Balmer, these lines are called Balmer lines. If they look at the emission or absorption here, they're called Paschen lines. These are names of spectroscopists of the 19th century. Okay, these lines here are in the optical portion of the spectrum in the region 4,000 to 7,000 angstroms. These lines are much higher energy. That puts them in the ultraviolet. You don't see them just by looking at them. Okay, so a star, in order to have strong absorption lines, has to have the atoms excited up to the first state. If all the atoms are sitting down here, it won't have any Balmer lines. It won't absorb them. So nothing. And the stars that are very cold can't excite the atoms. And so that means as you go from A down to M, the star is getting colder and colder and colder, and very few of the atoms are kicked out of this state. So the Balmer lines get weaker and weaker. All right. Well, that was not understood by the people who first classified the stars. So they got it wrong a little bit. But this is the modern classification, classified by temperature. The temperature is low, about 3,000 degrees here, and up here they're 20,000 degrees. That's pretty hot. 20, 30,000. All right? Okay, so let's look at this. These ladies did all this classification. They looked over there were thousands and thousands of plates, and they had plates that showed them the spectra. They had the spectra of many thousand objects. And looking at the information, they classified them. This was the Harvard classification. You all have dresses like this, I presume, hidden away in the closet. Your great-grandmother's dresses. Okay. So this was dated, this picture is, 100 years old. And that man is Professor Pickering, I believe. And this is taken at Harvard Observatory. Okay, so they had a noble goal. Annie Cannon, I think, is this one. She was more or less in charge. I think she was that one. Maybe it's that one. I can't remember. All right, anyhow, I used to be at Harvard, and I didn't see these people at all. They're all gone. This is a while ago. Okay. All right, so I want you to think about this one. How come the hottest stars show very few absorption lines? Why? Okay. Are the elements used up? Are the elements old? These stars old and they were formed before there were many elements? Are the atoms ionized? They've lost electrons, they're very, very hot. Or most of their absorptions in the ultraviolet, blue and green. All right, so think about this for just a moment. This is a hard question. I don't think most of you will get this, but try to answer this. All right? You can't do it yourself. You have to talk to your neighbor. Come on, talk, 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 talk. Have you taken, you understand this from the chemistry course?
I'm actually an astronomy major.
Oh, well, that's it. You're cheating.
Well, I haven't had any classes before, but I'm really interested, so I read a lot about it.
Oh, well, that's your cheat. Of course, everybody else is not. Come on, I don't hear enough talking here. All right. Now, it's not red. No, they're not used up. I mean, they got hot and all that stuff, but no, they're not used up. They're there. The atoms are present, but they're not shining at us. And it's not yellow. Sorry. It's not yellow because the stars actually are not old. They're young. The stars that are hot and incredibly bright, we will see that they're not old at all. They're incredibly young. Okay, it's not that it went away. And the absorption, no, they're not absorbing in the ultraviolet either. So it's really green. The atoms have been hit by the energy of the atom is so large that they collide and they knock the electrons off, and there aren't any electrons in the gas that can do any absorption. If there's no atoms of hydrogen, then it simply won't absorb in the atomic lines. So that's it, green. Okay. And furthermore, this is very strange. If you make a plot that plots, this is a very important plot. We're going to use this a number of times. This is plotting brightness going up and color going across. This is red, this is blue. It's backwards, the way astronomers usually do things, you know. But that's what it is. Low brightness here, very bright here. Now, the first thing that you notice is that the stars are not randomly distributed on this plot. They are not randomly distributed. Why do they take the form they take? That is the question that astronomers faced when they first knew this 100 years ago. Why are they this form? Okay? Now, what happens is that, first of all, there is something called a main sequence. That's this. The main sequence is where most of the stars are. There are fewer stars in this area here called white dwarfs, supergiants, and giants. And we'll talk about them all. The sun is, where's the sun? Oh yeah, okay, right in here. Okay? About in the middle of the main sequence line. Okay, so let me show you. Okay. Now, here's the main sequence, the whole thing. And these are stars nearby to us that you can use. You can measure the apparent magnitude, and you measure B, and you can infer from all these measurements, you measure what the absolute luminosity, capital L, is for that star. All right? Capital L's are drawn as the vertical axis. So it goes up to 1,000,000 times out of the brightness. This is in units of the sun. All right, so this is as bright as the sun to incredibly faint. They're really faint. So let's look at a few stars. First of all, Altair. It has, here's Altair. It has 10 times the luminosity of the sun. The temperature, instead of being 5,800 degrees, is 7,900 degrees. Radius of the star is 1.75 times that of the sun. The mass of the star is 2 times that of the sun. There's nothing, this stars, you see there's a huge distribution of the properties of stars. Stars are born with a certain amount of mass. The mass determines what happens. Once a star has a lot of mass, it's very hard to change it. So our sun was born with has one solar mass by definition. All right? And it evolves in a certain way. Now, here's some giant stars. For example, this guy, Deneb, has a luminosity of 330,000 times that of the sun, 9,400 degrees, 220 times the radius of the sun. It's huge, huge. 220 times bigger. And its mass, we don't know. We can't measure that mass because it's not in a binary orbit. So, unknown. All right, let's take a look at this. Betelgeuse. This is a very famous star. 52,000 times brighter than the sun. 3,000 degrees. It's very cold. The sun is 5,800 degrees. This star is half its temperature. Radius is 675 times that of the sun. That is big enough to include the Earth. So the Earth would not survive in such an orbit. I mean, if we were the distance of that from the center of the sun, we'd be fried crispy. We'd be inside the star. Gone. Eaten up. All right? Now, that's fine. But now let's look at these stars down here. These stars are in an area, this is 1/100th the radius of the star. And this is called Sirius B, very low luminosity, very high temperature, 25,000 degrees. That's the temperature. What is going on? Radius is tiny, the mass unknown. All right, let's take a look at this one. All right, here's one. The mass is 1% that of the Procyon B. This is 1% that of the sun. That's this radius of the Earth. This star has the radius of the Earth. It's 8,600 degrees. Very hot star. Very low luminosity. It's a low luminosity because the surface area of the star is very small. It's hard to get a big luminosity out of it then. All right, so all these stars are different. And so the question is, why are they so different? Here's a star, Beta Centauri. That is the nearby star. 150,000 times as bright, 27,000 degrees, 19 times the mass of the sun. And it's on the main sequence. The main sequence. So what's happening, we will see, is the main sequence has light stars here to heavier, heavier, and heavier stars. As we go up the main sequence, the mass of the star increases. That's the major thing, and we'll see how that runs. All right, so the main sequence is along this area. This area here, this is white dwarf area, it's called. This is the area of giants, and we'll talk about them all. Okay. All right, so the Hertzsprung-Russell diagram told us all about the stars, and it's very important that you understand what we mean by the Hertzsprung-Russell diagram. We're going to ask you to use it on tests. You have to know what I'm talking about on this diagram. This is really, really important. All right, so there's a wide variety of sizes of stars when you study them. For example, here is the sun. It's a G25. That's a classification of it. Lifetime of this star is 10 to the 10th years. Here's Spica, B15. A dwarf is a dwarf star because it's on the main sequence. Anything on the main sequence is called a dwarf star. I don't know why they're called dwarf, but it's just what it is. It's crazy. Sirius, an A1 star. This has a lifetime 10 to the 9th years, 10 to the 7th years. That's very, very short. 10 million years and the star is dead? Well, obviously, you're not going to evolve a complicated life form on any planet it has. You know, you can't do it. All right? Proxima Centauri is a very light star. It's very, compared to the sun, is very small mass and a huge lifetime. 100 times that of the sun. That is, you know, if you want to be comfortable old age, live on one of these stars. You'll be there forever, you know? Okay. All right, now, these stars are really pretty incredible. For example, Betelgeuse. Here is the orbit of Venus, this dotted line on the outside. Betelgeuse is much bigger than that. Inside, you draw again the orbit of Mercury. Here's the orbit of Mercury. Aldebaran, giant star. You go deep inside of Mercury, 10 times smaller. The Sun is tiny, G25 star. And then you go really, really small. Here's the Earth, Procyon b, white dwarf star that's the same size as the Earth. All right, so now this is something that was seen on. This was something that was seen. I don't think anybody thought you'd see this, but there are a class of stars known as Cepheids. CEPHID. Cepheid stars, and their brightness changes. Here is days, up and down, up and down, up and down, up and down, up and down. Now they're like a pot that is boiling hard, and it boils until the pressure in the pot gets high enough to lift the lid, and then it goes down. Then it boils some more, lifts the lid, goes down, lift the lid, goes down, lift the lid, goes down. This is exactly what's going on these stars. They are not stable. They have some instability on the surface and makes them oscillate. So up and down, up and down, up and down. All Cepheids do this. Some Cepheids have longer periods than others. That's very neat to look at them, and these are very useful. Okay, Cepheids, here's where Cepheids occur. This is some Cepheids. This is periods of an hour when they're right down here. Periods up here of days, and periods of weeks further up. Or not weeks, but several days. That's called the instability strip, and it applies to stars that are 1,000 times larger than, or somewhere between 100 and 1,000 times larger, or no, 10 to 1,000 times larger than the Sun. But that's okay. All right. Now, this is a beautiful sight. If you see the Pleiades, something is visible in the winter. Has the telescope pointed at the Pleiades? Is the Pleiades up now? I don't think so. All right. This is something you want to look at. The Pleiades and a globular cluster. This is known as a globular cluster, and we'll talk about what these are later. Now, notice this picture. Blue and red. Why is one picture blue and the other one red? This one is blue, and it contains stars that I know don't live very long. The red cluster contains very old stars, or could be old stars, that live a long time. So what do we infer from this? All right, so why are they red or all blue? Okay, the problem, if you look at the the triangles, the rectangles here, diamond-shaped. These are all stars that are together in a cluster that's known as H and Chi Persei. Those stars, we think, were born together. They're all the same age, in other words. A whole bunch of stars have the same age, and they are up here and here, and that's about it. NGC 188 has a color magnitude diagram. Magnitude, color that branches off like this. No stars up there. Why? Okay. Why is this what you see? This is a red cluster. This is a blue cluster. Why is it that way? All right. So what do the different this where it turns off is called the main sequence point. Main sequence turn-off point. Why is this one down here and this star cluster up there? Why? So this was something that astronomers wanted to know at the turn of the century, turn of the last century. All right, so these are all because the ages of these clusters are different. If they were younger, they would all look like this. If they're older, they look like this. So let's see how that works. Okay, just to remind you, what is the x-axis? Tell me what the x-axis is in the HR. It's known as HR diagram, Hertzsprung-Russell diagram. Tell me the x-axis, if you were paying attention. Color, temperature, spectral type, any of the above. Blue is any of the above. Luminosity is white. Okay, actually the answer is blue, any of the above. Normally it's plotted as spectral type, but that isn't really necessary. The blue color tells you, yes. Sorry? No. Let's here. Luminosity, total power is this one. And this one is, here, see it's labeled by temperature or by spectral type. This is down M, O, ranges around. So you can use either one, doesn't matter. Okay? And that's how you classify them. Okay. Now, I want to show you one or two more beautiful slides. Okay, so here's a region of the sky that just, here's a picture, and this is now dated by year. 300,000 years, it looks like everything. Everything's there. Let me turn this on. Okay. Bang, 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 bang. Oops, you wait 40 million years, and the stars are starting to disappear. You wait 700 or 800 million years, the blue stars are all disappearing. After 6 billion years, they're gone. There are no blue stars left. After 20 billion years, the only thing left is red stars. Why does that happen? Okay, now let's look at it through something else. Okay. Okay. All right, so let's look at this star cluster. When the star cluster is born, and it's 100,000 years old, the stars populate everything. Okay, now let me age this cluster. As it gets older, the stars start peeling off from here, from the main sequence. They're peeling back. 20 million years is peeled back. All the O stars are gone. B stars are still there. 400 million years, B stars are gone. Now we're starting up to the A stars. For 3 billion years are over here, 7 billion years. All right. So this is what happens. Now let me put on a star cluster, the Pleiades. This is what the Pleiades look like. And here is this line is the line of main sequence when the star cluster is born. So this is what you see the Pleiades to be. And you can date this by, I'm going to play with this line. Here it's starting to curve. Okay, 60 million years. If you wait 60 million years, it pretty much matches the HR diagram. This is amazing. Let's really think about this. This is totally stupendous. We have dated the age of that cluster. You look at that and say the whole thing was born 60 million years ago. That is pretty damn incredible. And that's how astronomy works, that we can actually do that. Now, how about, let's try another case. Here. All right, there's another one here. This is M87, a red cluster, M67, a red cluster. How old is this? Let's go on. Four billion years old. That's about how old our sun is. All right? And our sun is up here. Right there. All right? Another couple billion years, and it's going to turn off the main sequence, it's called. That's what it means. So you can look at that cluster and say, with confidence, the entire cluster is 4 billion years old. That's the date of it. Now, what is the assumption? The assumption is the cluster has been together for 4 billion years. They were born together, and they stayed together since. You believe it? All right. This is a really slick technique. It allows you to date the star. That is amazing that you can actually do that. Because, you know, you can't do it any other way. So now this required you to model. You have to be able to model, understand the physics, which we obviously didn't do. You got to understand the physics of the star, about when it's going to die, and all this, and go through the calculations of the lifetime. And it's a whole big industry of people who know how to do this, and the results are shown here. So it's not simple, but once it's done, that's done. Okay. All right. Now here's another thing we'll look at just quickly. What is happening on the stars? Let's just take it down to mass. Here is a star, and the inside the area of here is where the star is burning. The outer area is too cold to burn any hydrogen. So we're just going to burn it in the center. As it burns, burn, 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 the helium goes up, the hydrogen goes down. All right? And watch what happens. Helium goes up, 10 billion years, luminosity, mass of the sun, blah, 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 blah. Keeps going, 100%. It took 38 billion years for this star to burn through. That goes through the main sequence. Its luminosity is less than that of the sun. Let's try this. Let's try a 10 solar mass object. Burn, 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 dead. Okay? And that went 16 million years. The luminosity is very high compared to that of the sun. 10 solar mass star. That's really what goes on in the stars. The light ones burn fast. It's like, it's like a car. If you have a car and you have a big, heavy Cadillac, or what's a big, really monster truck that was built? A Hummer. A huge Hummer. It weighs a lot, can carry a lot of fuel, but still it doesn't get any, the number of miles it can go on a full tank of gas is pitiful. The miles would be equivalent to the age. It doesn't last very long. Whereas if you have a small car, really, really small, you don't have as much gas, it'll still be able to drive further before you have to fill it up. So the situation is these big stars, the big stars, do have more fuel in them, but they're burning fuel at such a prodigious rate that they won't last very long. That's the story. That's how it goes. In fact, for the homework problem I have you work out, it turns out that the stars, more or less, luminosity of the star goes as a fourth power of the mass. So if you have a 1 solar mass star, it'll burn at a certain rate. 10 solar mass star to fourth power of 10 is 10 to the fourth. And that means that instead of lasting 10 billion years, it's going to last 1 million years. That's it. So 10 billion, 1 million, 10 to the fourth smaller. Oh, no, 10, I'm sorry. No, it's going to last, you'll see, it's going to last 10 million years because it has more fuel. All right, so the heavier stars burn up fast. All right, so next time we're going to see what this does, talking about stars and how they move and what the star does for us, how the stars make elements, and et cetera, et cetera. Okay, I'll see you Tuesday. Then I want to make an introduction back there. Yokyung. Yokyung is going to lecture a week from today. I am going to be away for a day. I've won an award. She can tell you about it or read about it on her webpage, and I'm going to go pick it up in Munich. So